Welcome back to the Deep Dive. Today we're taking a journey into some unseen forces, the ones that really shape our modern world. Electricity and magnetism.
Yeah, absolutely.
We've gone through, well, a mountain of research, notes, tracking these ideas from way back, like their earliest discoveries, almost mystical stuff, right up to the complex circuits powering, your phone or your home right now.
And our mission really is to peel back those layers for you, to show the surprising connections, the practical side of these invisible forces.
Right. We want to turn these sort of abstract ideas into real aha moments.
Exactly. Show you how they're working behind the scenes all day, every day.
So let's kick things off. Where does this story even begin? Magnets, right? Nearly 5,000 years ago.
Incredible, isn't it? Ancient Magnesia, now Turkey. People found this rock, lodestone, and iron ore.
Just a rock. But it wasn't just any rock.
No, not at all. It had this weird, almost magical knack for pulling in small bits of iron.
Yeah.
Humanity's first brush with magnetism.
Amazing. So this lodestone. Yeah. It was a start, but probably not ideal.
Right. Natural magnets, they were fascinating, but limited. Odd shapes, weak sometimes, just not consistent.
So we needed something better.
Precisely. That led to engineering artificial magnets. Things like bar magnets, horseshoes, those little magnetic needles. Predictable shapes, reliable strength, much more useful.
Okay, so whether they're natural or man-made, magnets have these core behaviors, right? Two main properties.
Two fundamental ones, yeah. First, the attractive property. We all know magnets grab things like paper clips.
Sure.
But the interesting part is where they grab strongest. It's always near the ends. The poles.
Magnetic poles, that's where the power is concentrated.
Exactly. The magnetic field lines bunch up there, giving maximum pull.
Okay, that makes sense. And the second property?
The directive property. This one's really cool. If you hang a magnet so it can swing freely, maybe on a thread, it always settles down pointing roughly north-south. Always.
So that's how we get north and south poles. Yeah. The north-seeking pole and the south-seeking pole.
That's it. We call them N and S. And that simple fact gave us the magnetic compass. Think about how huge that was for navigation.
Totally changed exploration.
Yeah.
That little red end on the compass, pointing north, simple but profound.
And this consistent behavior, north-seeking, south-seeking, it leads directly to the basic rule, the law of magnetism.
Okay, what's the law?
It's simple. Like poles repel, and unlike poles attract.
Like repels, like opposites attract, just like, well, other things in life sometimes.
Maybe. But yeah, try pushing two north poles together. You feel that resistance, that pushback.
Yeah, definitely.
Now flip one, bring a north near a south. They just snap together. That force is the law in action. It's fundamental.
Okay, now here's something I think is really key, maybe a bit subtle. You told me repulsion is the sure test for a magnet. Why is that so important?
Great question. Think about it. A magnet attracts iron, right? Like a nail.
Sure.
But it also attracts the opposite pole of another magnet. North attracts south.
Okay, so attraction happens in two different scenarios.
Exactly. So if something is attracted to your magnet, you don't know for sure if it's just a piece of iron or if it's actually another magnet's opposite pole.
I see. Attraction is ambiguous.
Right. But repulsion, that only happens between two, poles, two norths or two souths. If you see two things pushing each other away...
And, 100% they're both magnets, no doubt.
Bingo. Repulsion is the definitive proof.
That's a really useful distinction.
Yeah.
Okay, and all this pushing and pulling happens within something called a magnetic field?
Yes. The magnetic field is that invisible space around the magnet where its influence works, where it can attract or repel.
Invisible, but you can sort of map it.
You can. If you move a compass around a magnet, the needle will keep changing direction, tracing out these invisible lines of force. It shows the shape and reach of the field. It's how magnets interact without even touching.
Okay, let's unpack this connection now. We've got magnets. We've got electricity. How do they link up? This feels like a big moment.
It was a massive moment. 1819, Hans Christian Ørsted, a Danish physicist, he noticed something, apparently by accident during a lecture.
Oh, what happened?
He had a wire carrying electric current near a compass, and he saw the compass needle twitch, deflect.
Just moved because of the electricity.
Yeah. The electric current was creating its own magnetic field around the wire. Before him, everyone thought electricity and magnetism were totally separate things.
Wow. So he realized they were connected.
He did. It was this profound insight. They're not separate. They're two aspects of the same fundamental force. Electromagnetism. That changed everything.
Okay, so electricity makes magnetism. How do we use that? Is that where electromagnets come in?
Precisely. That discovery is the core principle. Take some insulated copper wire, wind it into a coil, we call that a solenoid,
Solenoid, right?
and pass an electric current through it. Boom. It acts exactly like a bar magnet. North pole, south pole, the whole deal.
But the key difference is you can control it.
That's the genius. Turn the current on, you have a magnet. Turn it off, the magnetism disappears. You can even flip the current direction and swap the north and south poles. Total control.
Okay, here's where it gets really interesting for practical stuff. How do you make them stronger?
Good question. 3 main ways to boost the power. First, stick a piece of iron or steel inside the coil, a core.
Why does that help?
The core material concentrates the magnetic field lines, makes the whole thing much, much stronger.
Okay, core material. What else?
Second, just wrap more wire around, increase the number of turns in the coil. Each loop adds a bit more magnetic effect.
More turns, more magnetic muscle. Got it. And the third way?
Simple. Pump more current through the wire, increase the voltage, maybe add more battery cells. More current equals a stronger magnetic field.
So core, turns, current. Those are the control knobs.
Pretty much. And the type of core matters too, if you use soft iron.
Soft iron.
Yeah, it makes a temporary electromagnet. It's only magnetic while the current is flowing. Switch off the current, magnetism vanishes instantly. Really useful for things you need to switch on and off quickly.
Like what?
Think cranes lifting scrap metal. You need to pick it up and drop it.
Ah, right. Okay, so soft iron is temporary. What about steel?
Steel's different. It tends to hold on to the magnetism even after the current stops, so a steel core can create a permanent electromagnet, or at least one that stays magnetic for a while.
Interesting distinction. And figuring out which end is north or south. You mentioned a rule, not the clock rule.
Yeah, the clock rule works, but I find the right-hand rule much more intuitive for most people.
Okay, how does that work?
Imagine grabbing the coil with your right hand so your fingers crawl around in the same direction the current is flowing.
Okay, fingers follow the current.
Then your outstretched thumb points directly to the north pole of the electromagnet. Simple visual check.
Thumb points north. Got it. That seems easier. And where do we actually use these things? Electromagnets.
Oh, they are everywhere. Absolutely everywhere, often hidden. You know the obvious ones. Electric bells, motors, loudspeakers.
Right, things that move or make noise using electricity.
Exactly. But think bigger. Those huge electromagnets lifting tons of scrap iron in junkyards.
Yeah, you mentioned those.
Or in recycling plants, sorting iron out from aluminum or plastic. Very precise.
What else?
Even in medicine sometimes. If someone gets, say, tiny iron filings in an eye or a wound, a controlled electromagnet can sometimes be used to carefully pull them out.
Wow, really? That's delicate work.
It is. And then there are the motors inside everyday things. Your fan, your blender, your air conditioner. They all rely on electromagnets to create the spinning motion.
So they're basically fundamental to modern machines.
Fundamentally. Okay, so we've talked about the magnetic fields caused by current. Let's switch focus a bit and look at the electric current itself. What is it?
I mean, the flow.
At its heart, it's just moving electric charges. In wires like copper wires, it's electrons that are moving.
Electrons, the tiny negative particles.
Right. In liquids, it can be ions, but in metals, it's electrons. Think of it like heat flowing from hot to cold or water flowing downhill.
Okay, so there's a driving force.
Yeah, electrons naturally move from areas where there are too many of them, sort of high electrical pressure, to areas where there's a lack of them, low pressure, driven by what we call potential difference or voltage.
Makes sense. But isn't there something weird about the direction we say current flows?
Ah, yes. The historical quirk. Good point. Conventional current.
Yeah, explain that. It seems backward.
It is a bit. Back when scientists first started studying electricity, long before they knew about electrons, they assumed it was positive charges moving.
Just a guess.
Pretty much. And they defined the direction of current as flowing from the positive terminal to the negative terminal.
But electrons actually flow the other way, negative to positive.
They do, but the original convention stuck. So in all our diagrams, all our calculations, we still draw the arrow for current going from positive to negative, even though we know the electrons are actually moving the opposite way.
Huh. So engineers just have to remember that.
You just get used to it. It works out mathematically, but yeah, it's a historical footnote.
Okay. And we measure this flow rate.
We do. The rate of flow of charge is measured in amperes, symbol A. An ampere tells you how much charge, how many coulombs, basically, flow past a point each second.
Got it. Amps measure the flow. Now, does this flow happen easily through everything?
Oh, definitely not. Materials behave very differently. We basically group them into two main types, conductors and insulators.
Okay, conductors first. They let current flow.
Easily. Very easily. Think of metals, copper, aluminum, silver, iron, brass, steel. They all have electrons that aren't tightly bound to atoms. They're free to move.
So metals are like open highways for electrons.
Good analogy. And it's not just metals. Your body is actually a conductor, which is why electrical safety is so vital. Impure water, too.
Right. So what are insulators then? The opposite.
Exactly the opposite. Insulators strongly resist the flow of current. Their electrons are held very tightly by their atoms and can't move easily.
Things like rubber, plastic, wood, paper, glass, cotton, even pure distilled water. They act like roadblocks for electricity.
Which is why wires are coated in plastic or rubber.
Precisely. The insulation keeps the current safely inside the wire and stops it from going where you don't want it, like, into you.
Makes sense. Now, you mentioned resistance. Is that just another word for insulation?
Not quite. Resistance is more specific. It's the property within a material, even a conductor, that opposes the flow of current. Think of it like friction for electricity.
So even copper wire has some resistance.
A tiny amount, yes. But some materials are designed to have high resistance. We use that property.
How so?
Well, when current pushes through a high resistance, energy gets converted into heat, usually, and sometimes light. Think of the filament in an old light bulb.
It glows because it's resisting the current.
Exactly. Or the heating elements in a toaster or an electric heater. They're just high-resistance wires designed to get hot when current flows. We harness the resistance.
Clever. Okay, so we understand current, conductors, insulators, resistance. How do we actually build something useful with electricity? We need a circuit.
Right, absolutely need a circuit. And the key thing is it has to be complete or closed. Meaning there has to be an unbroken path for the current to flow from the source through the components and back to the source, all connected by conductors.
Like a loop?
Exactly. If there's any break in the loop, an open switch, a broken wire, an insulator in the way the circuit is open, and no current flows, nothing happens.
Okay. And when drawing these circuits, we don't draw batteries and bulbs realistically.
No, that would get very messy. We use standard symbols. There's a symbol for a single cell, another for a battery, which is a cells linked together, symbols for switches open and closed, symbols for bulbs, resistors, connecting wires.
Like a universal shorthand for circuits.
It is. It makes diagrams clear and easy for anyone to understand anywhere in the world.
Right. Now, when we connect things in a circuit, say multiple bulbs, are there different ways to do it? I remember hearing about series and parallel.
Yes, two fundamental ways. Series and parallel, and they behave very differently.
Let's start with series. What's that like?
In a series circuit, components are connected end to end, one after another, forming a single path for the current.
Like beads on a string.
Perfect analogy.
Yeah.
But here's the catch. Everything is dependent. If one component fails, say, a bulb burns out, it breaks the entire loop.
Everything goes off.
Everything. The current stops flowing everywhere. Remember those old-style Christmas tree lights?
Oh, yeah. One bulb goes, the whole string dies.
Yeah.
Nightmare.
That's a classic series circuit problem. Everything relies on everything else working.
Okay, so that sounds not ideal for most things. What's the alternative? Parallel.
Parallel circuits. This is how most things, especially in your house, are wired.
How does parallel work?
In parallel, each component gets its own separate branch, its own path connected back to the source.
So they're independent.
Completely independent. If one bulb burns out in a parallel circuit, the current can still flow through the other branches to the other bulbs. They stay lit.
Ah, that makes way more sense for a house. You turn off the kitchen light, the living room light stays on.
Exactly. One appliance failing or being switched off doesn't affect the others. It's much more reliable and practical for everyday use. That's why your home wiring is parallel.
Definitely preferred. Okay, we've talked about circuits. Where does the electricity actually come from, besides batteries?
Good question. We have several main sources, electric cells and batteries, of course. They convert chemical energy. Batteries are just multiple cells linked up for more voltage or duration. Dry cells are handy because they're portable, don't leak easily.
Right, like AA batteries. What else?
The big one is the mains, the electricity grid. That comes from huge generators and power stations, often miles away.
How does it get to us?
Through a complex network of high-voltage cables and transformers that step the voltage down for safe use in homes. It's a massive infrastructure.
Okay, mains power. Any others?
Well, generators themselves. Smaller ones can be used for backup power if the mains fail. They usually burn fuel to spin a turbine, converting mechanical energy into electrical energy.
Like for hospitals or during storms?
Exactly. And then there's a growing source. Solar cells or photovoltaics.
Solar panels.
Right. They convert sunlight, light energy, directly into electrical energy. No moving parts. Used everywhere now, from pocket calculators to satellites and entire solar farms.
Lots of options.
That-
Okay, before we wrap up circuits, safety seems crucial with electricity.
Absolutely paramount. Before you ever switch on a circuit you've built or even use an appliance, a few checks are vital.
Like what?
Make sure connections are right and tight. Loose wires can cause sparks or failures.
Okay, tight connections.
And critically, never ever handle electrical switches or plugs with wet hands. Water conducts electricity readily. It creates a path through you. Very dangerous.
Dry hands only. Got it.
And always use properly insulated wires. Never touch bare, exposed metal wires when a circuit is live. The insulation is there for your protection.
Good rules to live by. Okay, so,
Yeah.
wow, we've covered a lot. From ancient Greeks finding weird rocks
Yeah.
to understanding electrons flowing in wires, building circuits, powering everything. It's quite a journey.
It really is. And the key thing is how deeply linked magnetism and electricity are. You really can't have one without thinking about the other in the modern world. They're fundamental.
So intertwined. From that first compass needle twitching near a wire to, well, everything around us.
Indeed. And just think about how mastering these forces, understanding them, manipulating them, starting with something as simple as a compass-changing navigation,
Yeah.
all the way to wiring entire cities in parallel for reliable power.
Right.
It didn't just give us new gadgets. It fundamentally changed how human society operates, how we live, how we connect.
That's a powerful thought. Makes you wonder.
What's next? Yeah. What other invisible forces, maybe ones we only dimly perceive now, are we still on the verge of truly understanding? What might they unlock for us in the future?